So far we looked into links that could be error prone. We looked into heterogeneous cluster formations. But what if mobility plays a role, right? Mobility is something that could make your cluster more agile. The topology will change, which would cost you a little bit more of energy in maintaining the cluster. You have to understand when cluster will break up. You have to understand when they merge. So mobility will give extra cost. It's not that what we would like to look into that, because it's very complicated to make a lecture out of it, but just to give you a notion how mobility will affect the performance. So let's assume we would like to share content among friends, right? So one device has it all, and you would like to give it out to your devices. We had seen this in the NBC demo, for example, right? And the thing is, you are passing some of your friends for a while, and then they go out of range. That doesn't mean that this was enough time to really share the content, right? So we would like to share on the fly, that we give maybe several devices the content, partially or full, and then they start to change. Just to give you an idea how this works, I brought you a video, but before that, we assume here that there's things like service discovery and efficient transmission strategies, that we have them under control, right? And showing also the kind of coding comes into the picture. We started this to see how could we bring content to a device. So this is, when you look at state-of-the-art transmissions, we had here one receiver getting a video stream off. Then we switch on 5 receivers. And what you see is that after a while, the traffic can be quite high for already 5 receivers, right? So this was one of our demo sets up, and we could switch on one after another until the thing would break down. The thing is, what happens if we have such a cooperative device that could help? And then you see, these were the 5 devices. This is one device, and this is the traffic that one device would need if you do the cooperation. Why is this? So think about the multimedia exchange. Now you have one source, one content here on one of the device, and he will now move. And while you meet others, when you come in range, you can send out the content. That is not so easy. As I said, I brought you one example of a simulator that we had in the time. I hope it works. Yeah, these are some devices, and we let them move, right? And the circle is the coverage. And none of the devices has any content yet. We are just adding more and more devices. And now one of the guys gets a content. And while the others are in range, he's filling them up with information. These kind of information could be packets, right? The problem is that you would, for example, if you give packets and they would exchange later on what they're doing here, you would create a lot of duplicates. In order to avoid duplicates, what they are doing is they're getting the content and they're recoding the information they have. And with this, they're quite efficient. This was one of the demonstrators we built to look into, for example, impact of speed, the packet error probability, the range, the strategy, and then we look at the total time until everybody gets it. It's a picture, and you see that this is a little bit drizzling, the picture, and after a while it's getting in more and more. And we have to wait until all of these devices have the content. We can go a little bit closer, that you see that some of them, when they are green, they have the full information. There are not so many yet. There are 2 of them coming in now, and they are easily to do. But now we have a lot of things, and then exponentially you see how quickly it is done. Quite similar to a virus that is spreading, right? But I think that this in these times is very well known. Okay, now we built our own demonstrator to that for mobility. That the simulation is nice, but we would like to have something realistic. We took some phones for that. We had a big file of 4 megabyte, and we wanted to share it between devices, right? And there were different phone types, Nokia N97 and others, something you might not know. But the nice thing about it was they had a very good energy profiler. And these devices we put on Lego Mindstorms, so to let them move around. They had some good speed at the time, easy to program. The only thing is outdoor, they were quite fighting against some stones, as you will see in a minute. And also interesting what kind of mobility we should put in, right? Should they just walk around randomly? They must also not bump into things that were obstacles like other cars on the parking lot, or they should also respect some boundaries. We put a green line with a spray, some color around the parking lot so that they could see the green line and just go away from that. And then they had to carry the phones on a certain height to avoid the Frenzel zone of 30 centimeters, and that was it. So this was the very first test we did with humans. The problem is if you let these humans run around for 30 minutes, what happens is they cluster because they want to talk to each other. It's boring. In the beginning, it's easy when they walk around, but they got replaced by the Mindstorms, as you can see here, and we had to put them a little bit higher than 30 centimeters. Otherwise, if they're too close to the ground, the reception is very bad. And they were walking around. Oops, again, sorry. They were walking around now. Here you see the green line, right, where they should not go into over the line. And we had outdoor and indoor measurements. A measurement took 30 to 60 minutes, indoor 60, outdoor 30. Because of the ground, the battery from the robots were not good enough, right? And we generally got better connectivity indoors that had to do with the signal reflection from the walls. So what you see here, left is outdoor, right is indoor. We look at the number of connected neighbors. So how many neighbors can you expect? So as you can see in the beginning, there's a peak because they all started in the middle and then they could walk around. And the green line is the mean value, and the others are the values from the individual device. So here one of them has 3 neighbors, sometimes even here 4. The highest we could see were 5 after they really spread nicely. But the mean value here is something 1.5 around them. Indoor, it looks better. The mean value is twice as high. But even there, they don't see more than 5 at the given time. It's also interesting. But you see connectivity here is better than here, right? So the exchange will be here faster than there. And what we compared now is a TCP unicast versus a network coding UDP broadcast for indoor and outdoor. What you see here is that it looks like that network coding is way better than TCP, right? Especially if you look at the finishing order. So here we ask when all of the devices are done. We had 10 devices, one had the source. When the 9th device had it, how long does it take? What you also see is that the TCP was faster when we had 3 devices, less than 3 devices indoor or less than 2 outdoor. The reason is that one device is focusing on the other device and you get now my packets, right? While network coding is spreading out and investing into the future. And it's quite nice to see that the overall exchange time for outdoor is nearly factor 4 better, and here a factor 2. Okay, that is the mobility as we tried it out, but the impact on the mobility model that we put on the robots has also an impact. So we randomly let them walk around randomly. It's not so easily because there are different things what can do. One, for example, is a billiard model for a given area A, which was the parking lot size more or less, also the same form. We choose a starting point, choose any angle alpha, choose a velocity, and let the ball flip, so to speak. Or in our case, the velocity was all the same for the robot. They start, they go to the line, and then they go back. So the question is, how do they go back, right? Do they go back in like a billiard ball with a degree that they fall in, they fall out? And what would then happen? Would we visit all of the points, right? And yes, this will happen here. The border behavior is bounce back, delete and replace, wrap around. Therefore, it's like a billiard ball, more or less. So if you look at the distribution function over the time, you see every point will be at least seen once or with the same probability. We have done some evaluation already in 2004 about mobility models there. You can try it yourself with a Billiard mobility model. It's very easy here for in a Python script. And you can do the same with heat maps to see where the devices are. This is not the endpoint, this is the starting point, as you can see. And the problem is there might be some, with the Billiard model, there might be some tuples, then you don't receive all of the, you will not visit all of the points, right? This is clear. Good. So there are different ones like random walk waypoint mobility model. So you choose a starting point, choose an angle, choose a velocity, choose a time t, and then pause p. So you walk, wait a little bit, new angle, new speed, and start. So how would this probability look like? You see here that the inner parts are often seen, the outer part not that much, right? And this is not as good, you might ask, or maybe it is exactly your model. At least you see it's different. And here you will see a more dense scenario. So the devices would have more neighbors than in the example before, right? Even this, here's an example to how to make it in Python, if you like to look at it. There are more realistic ones, what is location dependent. So you cannot walk where boundaries are, like Manhattan grid, right? Then you would say, okay, I can only walk along the grid, right? Or if I have obstacles, right? This is also a little bit more realistic. And there's something other called Gauss-Markov mobility model. Another model that looks a little bit like this, right? I mean, who's walking around like this, you may ask, but can happen. And there's Attractor mobility model, which really was mapping nicely what we expected with the humans, that after a while they get attracted to each other, forming groups that talk to each other. And then you have these certain interest groups, right? There could be somebody interested in another person staying closer. So that means that you would also see more likelihood and more connectivity in these areas. So if you go to Python, there's something called PyMobility. A lot of libraries there, very good. You can try to use them for your simulations and see also the difference between them. There are also some other mobility models, so you can even say, why don't we just measure real people? Not so easy. We tried this with firefighters and the policemen, but it's not so easy to get the data from them because of privacy issues. And what we did then in the end is we just took mobility models out of virtual worlds, like a game like Quake 2. So we let people play on our servers for free. And what we find out is then the mobility inside such a model, right? The model has a clear impact, but we also looked into the number of connected neighbors that you could have in such a device. So this is a game where you have an ego shooter game, and you see that when they cluster, they have a lot of more potential neighbors to cooperate with. And while they were playing, we did our simulation on top of that. And if you then look at how they walk around, looks a little bit like the Gauss-Markovian model, right? We look at the partners they see right over the time. You can see it per device. Interesting is then also the angle. So in the random waypoint idea, you pause and then you make a random angle and you go away. In this case, you see that there's a clear tendency always to walk straight, or you change your angle in what you see. So the 120 degrees is exactly what you see on the screen. So this is what they're interested in, and they're running towards the direction from what they see. The rest is just panic mode when they are running away when they got hit or something like this. Colleague Christian Bettstetter from Austria, he also made a very nice overview about all the possible mobility models. I think you cannot do it better, so therefore it's a one picture out of his lecture, and then you can maybe detect which kind of mobility model you will need for your investigation. important to notice that mobility has a huge impact on the performance of any communication system. So it's always good to have a look at this. Last but not least is the question about the seating, right? I said it in the beginning for the football stadium. What is about where should I put my seating? Which of these N devices should my H cluster heads? And especially they can even move. Americans often, while there's a sport game ongoing, they go to buy a burger or whatever. So there's mobility. And so how can I maintain the seating? And how can I find an optimal solution, right? And that is not so easy. We looked into this for quite some time. And the idea for having a cluster head election, then you can say, okay, we know that the nodes are randomly deployed in the network, right? We can pick them out randomly, for example. Or we are looking out for the optimal solution. But if you look for the optimal solution here, if you test them out and then test everything out, the game is over before you found your optimal solution, right? So here a little bit quicker now, because it's I think the essence is just to understand what you should do. If you look at the overall number of tests you must do, it will be quite high, right? We have done this using something called genetic algorithm. And with this genetic algorithm, instead of testing all of the possible combinations, we looked only into a few of them, and based on a good one, we improved from there. If you look into a cooperation and evolution theory in the first lecture, you know more or less how it is. We are combining good sets and then moving up to a sub-optima. Okay, here you see what if you have, for example, 12 nodes and 4 cluster heads. And we would need 500 tests for an exhaustive search. That will take a while, the blue line here. Or we only need 40 tests with a genetic algorithm, right? Testing out 200 generations. So you see, that's faster, right? But if we would say instead of taking all possible sets, why not just saying, once I found something better, or it's sufficiently good, why don't I stop there, right? You see, for example, for the search here, he found something very good, right? Why not stick there? If you have a good notion about what is good, then you could really stop here. So we said, okay, is GA really good? If you compare it to a random approach, and we give both approaches the same time to do tests, and you see here that the GA would do around 70 tests, while the random one would only take 55 tests, and this is the same time because the random guide is doing will always take more, while the genetic algorithm is improving over time. And this gives you a 5% gain, right? But this is not really what we are looking at. Interesting is if now mobility comes into the picture, and we want to find the next best solution. And this is, for the random, it will undergo the same search again. Even though it has to be restarted, it will do a random approach again. But with the GA, we only have to say we had already a good one. We are searching close by in recombining in a generic way the different optimal things we have found so far, and can quickly get a new, a good setup for the seeding. And this is the rest. I leave it up to you for the reading at home, where you can see the cooperative content sharing, where we say what is the best strategy to form cooperative cluster and maintain them in the presence of mobility, right? And there are some findings, for example, that lower cellular rates are good for us because it gives us more time. When you have high data rates, then you have to be very quick in exchanging it or having at least larger files. And then looking into this genetic algorithm a little bit more in theory. And this is, I leave it up to you. The important part is, if you compare them, is really the number of tests with genetic algorithm compared to the exhaustive search is way better, as you have seen before, right? And then you see the number of generations before GA convergence, and with different values. And you can see that we can, after mobility kicks in and the topology change, we can quickly adapt to the changes that are there. So today we have looked into the real energy gains that we can have, and also underline why this is important for cooperation. We can lure people into cooperation. The more cooperative partners we can find, the better for the gain. And we have seen that also the technology plays a bigger role. The more data rate you have on the short range, the better it seems to be, because this factor Z plays a role. And the rest, you just find out that it has to do with the technical parameters from the data sheet of your technology. We also relaxed a little bit this analytical model in the beginning with error-prone links. For the football stadium scenario, we looked into the mobility, as well as we also looked into heterogeneous group sizes. And last but not least, I showed you a little bit how can we deal with seeding of the content into the right devices in order to bring up the cooperation. That's all for the 5th lecture in cooperative wireless systems. So thank you very much.